Hello, I'm Federico Levi from Phys Freiburg, and let me tell you something about our work on quantum coherence. Here on the whiteboard behind me, there are sketches of two different physical systems. The first one is a multi-slit experiment, where now we have a source of photons. These photons are crossing a multi-slit grating and then impinge on a screen. Here this is a sketch of a pigment-protein complex, where these tiny items are chlorophylls, and this chlorophyll wire the excitation which has been absorbed from the sunlight from the input side of this protein to the output side. These two are very different systems, but they both feature the same phenomena, which is transport. Here it's photon transport, here it's excitation transport. One can then imagine many other examples of physical systems with transport, which will all be described by the same formal framework. Classically, the photons can take either of these paths with a certain definite probability. This would give rise on the screen to a smooth probability to find the photons at a given position. On the other hand, quantum laws allow for the superposition of different paths as the ones depicted in red in our sketch. If this is the case, then we would refer to this situation as the photon is coherently delocalized over two path alternatives in our system. Now, in this case, one would see an emergence of an interference pattern on the screen, the red one here. And with respect to the classical one, which is the green one, then this interference pattern may lead to an enhancement of the probability to find the photon in a spot, or to a suppression. The strength of this enhancement or suppression strongly depends on the number of paths where our photon is coherently delocalized over. So, for instance, if the photon were exploring 4 paths at the same time coherently, then we would have a much stronger enhancement than in the case of just 2 of them. All these concepts can be translated into the pigment-protein complex example, because here we have the excitation which crosses this protein following a certain path. Different path alternatives can then interfere in the presence of quantum coherence. This would give rise to the same interference we have seen for the interferometer, and this in turn influences the probability, by enhancing or suppressing it, the probability that the excitation is successfully transported through the protein. This is all for the case of a perfectly coherent evolution, but in reality one has to deal with noise. Noise tends to decrease quantum coherence and therefore smears out this enhancement or suppression of the transfer probability we have been discussing. Therefore, in reality, one has to deal with an interplay between the coherent delocalization originating from quantum coherence and the incoherent delocalization which arises from noise. This interplay crucially influences the transport dynamics, and it would be therefore highly desirable to be able to quantify and distinguish these contributions. And this is exactly the objective of our paper. There we introduce a quantitative theory of coherent delocalization. This allows us to define a set of measures which we can use to characterize the coherence properties in transport processes.